Hey everyone, what we want to do here is try a couple example problems to show you how to set up conservation of energy and to solve for whatever the problem might give you. So let's make this be our first problem here. Got a milk jug that's on top of a shelf. It falls off the shelf and reaches the floor. Let's say it's a height of 5 meters above the shelf. The question would be, how fast is that milk jug going when it reaches the bottom? So I'm going to set these up with an LOL. Two different ways. I showed two different versions of the LOL. You can pick whichever version you'd like, and the whole point of using the energy bar graphs is to help write yourself equations for this scenario. So let's go to the bar graph. Looking at my scenario here, I can see that there was no kinetic energy in the bottle at the beginning. There was no spring involved. We're not going to deal with any frictional forces or work done by external forces. So in my system here, I just had the Earth and the bottle, and originally it was above the ground, so there was some gravitational potential energy. When the bottle reached the floor, if we make the bottom of our floor 0, that means it's got kinetic energy, but has lost all its gravitational potential due to its height. And there was no spring involved, so we don't have to worry about that moving either. So in this case, the energy was in the Earth's gravitational field and turned into kinetic energy of the bottle right before it hit the ground. Looking at your bar graph here, I know that all I have to do is set gravitational energy equal to the kinetic energy on this side. So let's go back to the problem. Gravitational energy equals the kinetic. Looking at what we have here, mgh is going to equal 1/2 mv squared. I do have a mass on both sides, and solving for velocity at the ground is 2 times gravity times height. So my height was 5 meters. Gravity we can round to 10, and 2 is just a number. Multiply all three of those, and you get from a height of 5 meters, that object's going 10 meters per second after it has fallen that height. Here's scenario 2. They're giving me the mass of the block, they're giving me the compression in a spring, and it looks like that spring is uncompressing, so it's trying to get rid of its stored up energy, put it into the block, and then that block rises up a certain height along that track. So I use a second type of bar graph to see how we'd set this up. And we can focus on two locations. We can make position A be the start point right here, and we could look at either spot. We could look at right when the spring is uncollapsed, or we can look at the location when it reaches its highest point. So let's go try and set up both of those. I'll do this in different colors so you can see. Okay, so with this one, we have the spring that is fully compressed. So if we want to talk about what's in our system, instead of having that O like we had on the LOL, here it's just asking what objects are in the system. So in our system, we've got the Earth, we've got the block, and we've got the spring. We'll keep friction out of this so there are no non-conservative forces around. The potential energies here are going to be gravitational and energy in the spring. And any external forces, we're going to say that there was no one outside the system, so it'll make that a little bit more straightforward. Okay, so going down our list, kinetic energy in the beginning was 0. There was no height energy off the beginning. The spring was compressed, so we'll make that in green here, saying that you had spring potential energy, no non-conservative forces or work by external forces. And at the end of the spring's stretch, we know that it was moving, so there was kinetic energy. There was no height involved, and the spring was no longer stretched. So really, just from the spring being unstretched to the endpoint, we can figure out its speed by just looking at energy in the spring turning into kinetic energy. So 1/2 kx squared will equal 1/2 mv squared. There's a half on each side, so I can knock out that. If I want to know the speed afterwards, so plugging in the values we know from the problem before, the K value was 500 newtons per meter, the stretch was 20 centimeters, and the mass was 2 kilograms. Putting all those numbers in, you end up with a velocity of the square root of 10 meters per second. So that's the speed that the block was traveling once it left the spring. The object starting with the spring being compressed and ending at the top of the hill. And this is all that would change. At the top of the hill, there would be no kinetic energy. The spring would not be compressed anymore, and now we'd have So 1/2 kx squared turns into mgh. If I want to solve for height again, divide by mg, and you're left with the height. Punching in your values, you get a height of about 1/2 meter. So if you do all your work, you can just focus on the beginning when the spring is compressed and the end when the object has reached its highest point and get a 1/2 meter of height. Now, they may ask you how far it travels up the track. All that you have solved for here is the height. And the problem also told us that this was a 45-degree angle. So the 45-degree angle and the one leg of the triangle understood already, you should be able to use your trig to figure out what the length along the track would be, right here in blue. So when you solve for height, that's only vertical height from our 0 point that we took to be the ground where the block started. Let's try another one. In this example, we're trying to find the height and final velocity of a soccer ball once it is kicked off this roof. So they give you a height above the floor, they give you the speed and the angle that the projectile is launched at, and you can absolutely use all of your kinematics for this. However, I'm going to say that energy is probably going to be a little bit easier for you because you don't have to worry about the time of flight or anything like that. All you care about is the start point of that ball and whatever end point you're interested in. So let's go with the first one. Let's find the final height of the ball. The way I'm going to do that is set my 0 line to be right here, right at the ball. So the 0 line there, I'm going to solve for how high does the ball travel above that 0 line that I have already set. So let's do our LOL. Okay, so the moment you kick the ball is going to have kinetic energy. The gravitational energy is 0 because of the location I picked to be my 0 point. No springs, no drag forces. The work was done by a person to give the ball kinetic energy, so if you want to say that actually that kinetic energy is the work done by the person's kick, absolutely you can. I'm already going past that point when the ball was kicked. I've got the ball and I've got the earth. Only things that are interacting with each other. At the end point, I know there's no spring, so I'm going to say 0 to that. But here's where people get tripped up with this. I want to find the final height of the ball as it goes through that parabolic path. So at this location, everyone knows that the ball stops. It does stop, but in which direction? It stops vertically. It does not stop horizontally. So you've got to keep some kinetic energy in the horizontal motion of the ball. And you also have some energy in the new height that it has gained. So when you look at your setup here, you've got kinetic energy turning into kinetic and gravitational potential at the end. All the energy that was in the ball, some of it goes to the earth, but some of it stays inside the ball and keeping the ball moving through its parabolic path. So let's go set up the formula. So here's our setup. Kinetic in the beginning equals our kinetic at the end plus the extra height energy that we've given the ball due to its new height. So looking across this equation here, the initial kinetic energy, the final kinetic energy, and the gravitational potential energy all have mass in them. So we can actually take the mass out of every single equation and not have to worry about it. The initial velocity was 16 meters per second at an angle. The nice thing about this, as compared to when we did this with kinematics, is all I care about is the real speed at that moment. So you can just use 16 meters per second. Over on the final side, the velocity at the highest point is just the horizontal velocity. So really you just have to care about how fast it's going horizontally, which comes out to the 16 cosine of the angle meters per second. We'll square that value. Plus 9.8 meters per second squared times height. So we have everything we need except for the height. You end up with a height of about 9.8 meters. And you might put that in a WebAssign, and WebAssign will give you the big old red X. And that's not what you want to see. Because the question might be, what is the height above the ground, not the height as it's going through its trajectory. So if you go back and look at the problem was already 12 meters above the ground. So you make sure you add in that extra 9.8 meters of height to get your final height of around 21.8 meters. So that's what they're going to ask you to find the height above the ground. Now the final velocity of the ball would probably be when the ball finishes its arc path and reaches the ground over here. So in this case, when the ball reaches the ground, I'm going to make my zero line down here. It's going to change my LOL a little bit because all I have to care about is an extra energy at the beginning and only one energy at the end, which will be really, really nice for us. Okay, so here's the other half of the soccer problem. Some of the objects in the system here were the ball and earth for our system. No non-conservative forces, not dealing with air friction or drag or anything. Really the only potential energy here is gravitational and external forces. There was someone that kicked the ball, but we're going to assume the problem starts right after the kick, so the object's already moving. So if we go through our list again, remember we changed our 0 point. Our 0 point is now at the ground. So looking over here, we've got kinetic energy, we've got gravitational energy. We do not have any spring, don't have to worry about any frictional forces or work done by external forces. And when we reach the ground, we've got speed for sure, no height, and no spring. So going through the energy bar graph this way, you can see that those two energies in the beginning must add up to my one energy at the end. So when I do this, I can set up my mathematical equation. And looking at what we have here again, the mass is the same all the way through. And things I know is I know my starting height, 12 meters. I know my starting kick speed, which is 16 meters per second. And all I'm going to look for here is the VF. So after all said and done, when the ball reaches the ground here, it'll be going 22.17 meters per second as it strikes the ground. Don't have to worry about any components. Don't have to worry about time. The ball was in the air. The question was just about speed as it reaches the ground. So energy is a really nice way of solving a problem like that. So another example problem we could look at is something like this. We've got a block falling onto a spring, and we want to know what that maximum compression is once it hits the spring. So we'll set up our energy bar graphs here, whether it's LOL or the other method. I'll leave that up to you, but I'll do one method. If you want to try the opposite and see if you get the same setup, that's fine by me. So if I look at the beginning here, the first thing I can look at is that height that the block is above the spring. And if I look at that height, I know that I've got gravitational potential energy. And when you make your zero line for this one, it can be a little tricky where you'd want to put it, but for me, what I would do is I might put the height being 0 when I'm out of all gravitational energy when the spring gets to its max compression. So I might put that right around there. So I'd say, okay, there's my 0 reference line. My 0 reference says that my height is 0 when the spring is fully collapsed, and so we can set up a problem right from there. Some questions may ask you, hey, what's the speed of the block right as it hits the spring? So for that, I'm not even going to go through that because we've done that a couple times now. I know up here you're dealing with gravitational energy, and if you make this your 0 line, the block has kinetic energy right before it strikes there. And I know you can set up mgh and 1/2 mv squared to solve for that speed. But what I want to know is the compression of that spring. So let's go to our energy bar graphs. Going with our system here. So we got the box spring earth system here. In the beginning, no speed. Spring hasn't been compressed. Won't worry about any external forces or non-conservative forces, so everything is in gravitational potential energy. At the end, at the very end, when the spring is maximally compressed, the object will stop moving. Gravitational energy will go to its lowest point, and we're now dealing with our spring energy. So technically, the energy started off in the gravitational field, went into the box, and then didn't stay in the box because it eventually leaked into the spring and stayed with the spring to give it its max compression. So let's set that up. Equation here, gravitational energy must equal spring potential energy. Alright, so in setting this up, mgh is our gravitational energy, 1/2 kx squared is our spring potential energy. We could be given the spring constant, the mass of the block, we know gravity. The question is, how far has the spring been compressed? And here's my before situation, and here is my after situation. That block has traveled a height right here. It started off above the spring, and the maximum height it fell was all the way down till the spring was compressed. So technically, it could have fallen this original height here. I think the problem gave us about 15 centimeters. And then it's going to fall whatever this compression X is here. So technically, your height is mg with the 15 centimeters plus the X of the compression. And over here on the spring side, I've got my 1/2 kx squared. The unknown here is that compression, how far that spring has been compressed here. So if you set that up, you're going to end up with a quadratic. You're going to have something with x squared, something with x, and a number. So if you go through your quadratic equation, you're going to get two roots. And using the variables that were given to us, then our spring constant is 5,000 newtons per meter. Got a mass of 10.2 kilograms, and we know the gravitational field strength. So let's put those values in, and here are the two roots that spit out. So when you do this, your y comes out to two different roots, 0.1 meters or negative 0.06 meters. And if you're looking at the way we defined our height, having a negative height would be something having the spring stretch higher up than it normally was. So 0.01 is the height that makes sense for our compression here.